So we're actually going to resume from where we left off on Tuesday, talking about the dplyr package and using it to manipulate data sets that you've already read in. We'll talk about reading in data next week. And we talked about, so we're going through the R for data science. If you go to section 5, it's a transformation, and we're using the NYC flights library, which has the flights object. That's a big 330,000 item list of flights. And in general, we talked about the 5 different functions, or sorry, we talked about 4 different sort of core things you can use with dplyr. The filter, which is used to select rows given on what their columns have, to reorder the rows with arrange, to sort of trim down your data set to all the rows but certain columns using select. And we left off playing a little bit with Mutate, which creates new columns. Today we're going to talk about Summaries and how you can combine a whole bunch of these together in a nice sort of data workflow. So I actually still have the code from Tuesday. So we installed the packages that we needed. I thought dplyr already brought in Tibble, but just to be sure, I loaded in Tibble as well. So we loaded in all the packages, and then we took a look at the flights, which we can see here is going to be a big data set. Because it's a Tibble, we could also just say print flights, and if I resize this window over here, it should show us a nice output of the first little bit of that big data frame, or that big data set. Then we went through some examples of using filter. So this is an example of using filter to select down to just those rows for which month equals 1, and just those rows for which day equals 1. So January 1st. So running this will yield an object called flights2 that if we looked at would have all the January 1st flights. And you can put any number of sort of selectors here. So here there's 2, month and day. Had an example here where sort of demonstrating, first of all, how to create your own little Tibbles for examples. And then this example was just showing that whenever you encounter an NA, it will sort that NA right to the bottom, any rows with NAs right to the bottom. Or no, sorry, that was talking about arrange. Whenever you're using filter, it will always toss any rows with an NA in the column that you're using to filter on. Then we talked about arrange. Again, usually I don't use arrange much because I don't look at my data like this. Usually I'm doing things that we'll get into, which is using summaries and things. But if you want to look at your data, you can use arrange, which will sort the columns you give it as sort of the second through nth arguments here. And you can use by default, it'll order them ascending. You can use the desc function to tell it to order those descending. Select was the way that you can toss columns or keep certain columns. As we got into that, we started exploring some of the string matching functions that come with dplyr. So contains in a string that will grab all the columns in the flight data or flights data set that contain the string dep anywhere. There was also starts with. So it grabs those ones that just start with and of course ends with, and that's going to be nothing. So none of the columns. It's interesting. It says 330,000 rows of 0 columns. So that's interesting. I would have thought that it would have just said null or something.
How does R behave when you have an empty cell?
That's what NA is. So we will, when we talk about reading in data, we'll talk about how to, so if you have, say, a plain text file where or even if you had like an Excel spreadsheet that you exported as one of the export versions is, or export types is CSV, comma separated values. That's a really common data type. And maybe Excel put NaN there for missing values. R would be expecting to see NA as a missing value, so you'd need to tell R that whenever you see the string NaN, interpret that as NA. But we'll get into that more when we deal with reading in data. Now we'll turn my phone off. Yeah, using select, you can use sort of string matching functions to sort of parse the strings to select more flexibly. We then wanted to deal with mutate. It was useful to create a sort of a smaller data set that we could look at. So we used the select function. We, again, telling it to look in the flights data set, keep all those that end with delay, and keep distance, and keep airtime. So if we run this, and let's say print this, we should see 4 rows, the 2 that ended with delay, and then 2 more distance and airtime. And we ended off talking about mutate, which takes in a data frame. So we're using the sort of subsetted data frame, flight small, SML. And we're telling it to create a new column called gain. And in that column, put the result of this computation. So this computation involves 2 columns that were already in flight small. Ditto, we asked it to create a new column called speed and put in it the result of this computation. This computation involving 2 columns that were already in the data set. But furthermore, we showed that we could actually get a new column, gain x speed, where we were asking it to do a computation on 2 columns that weren't already existing in the data frame, but will exist by the time that mutate gets to this sort of line here. So it will get to this line, create this column, get to this line, create this column, and it will get to this line, and it will create that column using the 2 columns that it just created. So you can refer to columns. When creating new columns, you can refer to columns that already exist in the data set, or columns that you are creating sort of in that same call to mutate, which is really nice and flexible. Here's an example of creating a column where you were sort of asking a logical statement about each row. So you're asking, for each row, is the value in the distance column greater than 1,000? So let me actually run this and we'll see the result. And that will, oh, it didn't show that last column. So we get all those. So we get the gain column, the speed column, the gain by speed column, and this dist column that is just asking for each row is the thing that's way over here in distance greater than 1,000. So true, 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 false, false, true. That corresponds to that logical test. All right, so mutate is when you want to just add new data. You're not really summarizing anything yet. You're not really sort of compressing anything. The resulting data frame has the same number of rows as the original data frame. You just are adding new columns. So each row gets a new thing at the end or in a new column. So next we're going to talk about summarize. So if I can go to there and we'll scroll through the mutate. One sort of tweak on Mutate is if you only wanted to keep these new columns. So if I didn't want the first 4 ones, but needed them to do the computation in the first place, so I only want to keep these last 4, transmute would yield just the new columns. It's kind of like doing a mutate and then a select to keep only those new columns.
So it will do the measurement and make that keep what you want.
Yeah. In the manual itself, he goes through a number of different useful sort of data transformations like modulus and things. I don't think we'll typically get into those. All right, summaries and grouped summaries. So the way summary works is that if you have, I'm gonna pull this over. Let's summarize. Right. I wonder, is summarize an actual thing? Yes, so you can spell it I-Z-E or I-S-E. Either way, doesn't matter. Just like all of the dplyr functions, it takes as its first argument a data. So let's do data flights. And as the second argument, it's asking for you to sort of put the name of a new column that you want to make, and then on the right of the equals is some computation that you're going to do on the full data set to be stored in that new column. So it sounds kind of like mutate. You're going to do some computation on the existing columns, but critical is that the previous computations we had, if you had a column of, say, 330,000 elements, the result was a new column of 330,000 rows. This one is going to yield a single value. So mean will take in this column depth delay of 330,000 rows and compress it to just one value. It's going to get the mean for that entire column. So summarize differs from mutate in that it sort of ends up collapsing data. You end up having fewer rows afterwards than you had in the first place, whereas mutate and transmute yield the same number of rows as earlier. So I'll just copy this. So you've got mean, depth delay, na.rm equals true. I guess I'll be consistent with my style guide and put these on separate lines. So if I run that, it's going to create a new Tibble dataset that has just a single column called delay, and in that column will be just a single value representing the mean departure delay for the entire dataset flights. So it's actually not a super exciting sort of data object Tibble with one row and one column. That's the result. I could have, well, yeah. More useful is when you start combining summarize with grouping. So that's what we're doing next. So I might as well copy that. So I'm going to use the group by function. And I'm going to create a new object. I'm going to use the group by function on the flights data and assign the result of that call to group by into a new object. So flights, or I guess in the example he called it by day. Group by. So again, the dplyr function, so it wants a data object as its first thing, but the second argument is, second through nth argument is the variables that you want to be sort of grouping variables. So let me actually here, let's call it by day. So I'm just going to put day there. So what this is going to do, internally, it's going to create a representation of the flights data set where it knows any subsequent operations using Summaries will get a summary for each unique value in this day column. So let's just run this, and there's no output. It's assigned the result of group by into this object called by day. So let's actually take a look at by day. Print by day. And it's a table. It's got the same number of rows and same number of columns as the original flights data set. And it looks exactly like the original flights data set. The only difference is that there's this new sort of row in the output in the description here, where it's telling us that it's grouping by the day column, and there are 31 unique sort of elements in the day column, which makes sense because it's the day encodes the date. So now we can use that by day if we do a call to summarize data equals by day, and I can just copy what I had above. I'll create a new column called delay. And now we'll see we've got, where before we had a 1 by 1 table, now we've got a 31 by 2 table. So the two columns, there's a row for every day that it has found in the day, unique sort of level of day it's found in a day column of the original flights data set. And there's one column indicating what sort of row that day that row corresponds to. And then there's a column called delay that we created that represents the mean of the departure delays for that particular day. So by creating this grouping, we've managed to now get out the mean per day, which is a little bit more useful than just the mean of the entire set of data. So you can start conditioning your data on sort of things of interest and computing these summary statistics very quickly using group by and summarize. I can actually have multiple sort of measures being computed. Measure meaning I'm asking for the mean of the depth delay column. Maybe I am interested in the variability of these delay times. So I'll maybe rename this mean delay, and I'll create another one where I copy this, and I'll say SD delay, and I'll use the SD. Again, these names are human meaningful, but I could have, the fact that I have the word mean here doesn't tell R anything about what it needs to compute. If I put like, R will run this bit of code, but the human label of standard deviation of delay wouldn't be accurately describing what's there, which would be compute the median delay. So if I run that, I should get now a table with, again, 31 rows, one row for each day that's in the data set. But now, in addition to mean delay, I get the variability of delay, the standard deviation of delay. And that might be a metric that I'd be interested in. So you can put any sort of number of metrics, any number of computations on the original data set in there, and that will just yield a new column. Sure. So what this means is that it's going to look in the flights data set. It's going to find all the unique sort of values in the column that I give it here. So it's a day column, so it's going to find all the unique days. And it's going to sort of group them together so that any subsequent use of the summarize function will automatically do whatever computation we're asking of it independently for each level of the thing that we're giving it here. So we're using day here, so it's going to see that there's a bunch of days with a 1 in the day column. There's a bunch of rows with a 1 in the day column. When it does a mean, it's going to do a mean first for all the days that have a 1 in the column, then for all the days that have a 2 in the column, then for all the days that have a 3. So here's the mean for all the days that have a 1 in the that column. Here's for all the days that had a 2 in that column, etc. So
It's technically taking the whole years of data and all of them were done in the first of the month.
yep,
So it is.
yeah. So this ignores year, it ignores month.
Exactly.
If we wanted further, like, I guess, conditioning of our data, we can add more variables here. So if we wanted to do computations for every day of every month, but still ignoring year, because that's another variable, there should be, well, if I had just condition by month, it's going to yield, and run all this. It's going to yield 12 rows. So that's the monthly mean. If I put day back in here, we're going to get a mean for every day for every month independently. And really what that means is that if you had multiple years, it's going to average across the year. So if you had a January 1st, so this is January 1st. If you had a January 1st on 2013 in the data set and a January 1st on 2014, January 1st in 2015, this value here will represent the average across those 3 data points, those 3 rows. I think if I did day, month, year, often, and in fact, there's each day in this original data set has lots of flights. So this is still, even if you did day, month, year, it would still be averaging all the flights that happen to happen on that particular calendar date. Does that make sense to folks that you can, this group by doesn't change, doesn't actually like do anything to the data other than sort of set a little flag for when you then subsequently do any call to summarize. It will do what computations you've sort of specified here to the pieces of the data independently, where the pieces are sort of defined by your grouping expression here. So let's see, what further? So far I've been showing you guys this where I have been sort of creating objects and I'm always giving it this .data argument. There's a way that dplyr is set to work that actually makes it, well, certainly less typing, and it can be argued that some people find it easier to understand a sequence of operations. So, for example, I had to create this thing called group by and then use it here. I had to think about like what name I wanted to name this object. Wouldn't it be great if I could just like do it all in one go? One way of doing that is to I actually wonder, can I, instead of storing the result of group by away in this object and then using this object here, I could put that call to group by right there. We've already seen scenarios of where you call one function inside a call to another function. But that ends up being, you need to sort of keep track of the nesting of the functions then, and that's a little less than ideal. So I'm going to leave it like that. In fact, I'm going to write a little bit of code below. So instead of having the group by being assigned to something, what you can actually do is use this funny character. It is a percent sign and then the greater than symbol, so the sort of rightward pointing comparison, and another percent sign. So it's this funny sequence of characters. And let me actually triple check that that's the right one. Yeah, it is. Okay. So I can do this call to group by, and instead of storing it back into a new object, I'm actually piping it to the next thing, which will be a call to summarize. I'll copy this whole thing. And I'm just going to put it on a new line. When
We did not call group by data, right?
Yeah, no, we haven't stored the result of this call to the group by function. We haven't stored its result anywhere. But by putting this character string here, R will know that you want to use that result and give it to the next function, pipe it to the next thing that you're going to use. So this has to be the last thing on this line, but the next one can start on a new line. Now, since I'm using the pipe operator here, I no longer have to tell Summarize what data to look at. It's automatically going to look at the pipe, what it's seeing, receiving through the pipe. So that actually reduces your typing a little bit. You don't need to type a name for this thing, group by, and you also don't need to then tell Summarize to use that thing that you just created. You can just say, run the group by function, pipe the result into Summarize, and Summarize will automatically know that the data set that it's dealing with is whatever the command before it piped to it. So this has become sort of a bit of a popular way of expressing things because it's sort of, when you're looking back at your code, it makes it a lot easier to see like what are the individual steps of the transformations rather than having sort of creating new object, transforming, putting that into a new object, and transforming along. You also don't need to come up with nice, unique names for everything. Similarly, group by can actually take its, can receive from a pipe the data set that it's supposed to be using. So instead of having it group by and giving it the flights data, we can do this. Flights. So it's kind of clear in this expression that we're starting with the flights data set and then doing a grouping and then doing a summarize. So this is what you'll sort of more typically see with the use of dplyr. I'll run it just to show you it gets that same results that we had before. This is kind of similar to when we were dealing with ggplot. I taught you guys creating each object and then at the very end adding them all, creating each layer, putting it into an object, its own sort of unique object, and at the end adding all those objects together. Add in ggplot is like pipe in dplyr. In fact, the author of dplyr is also the author of ggplot, and it was only more recently that the pipe operator or idea came about. And if that idea had existed when he authored ggplot, he says he would have authored ggplot in a very different way. He would have used the pipe. But as is, you use plus to add together objects in a ggplot object. For data sets, and sort of data transformations, we're going to be using the pipe operator. So kind of quickly, so this is that section where he shows that you can create these individual objects, so a grouping object, and then a summarize object, and then maybe even a filter object at the end. He uses the analogy to ggplot where you can create these things and add them together to show that you can simplify things by piping them all together. Here, sort of the result of this whole thing, the whole sequence of pipes, gets then assigned back into some object called delays. So,
What is an ARM?
well, this goes back to the very first. In fact, we used it here when we in both of these. I think this data set might have some NAs in it. In fact, let's try. So if I take this off or comment it out, yeah, it will. Let me see. Did we get any NAs? Yeah. Okay. So there is some missing data in this data set. If there's missing data, you can't compute a mean, or when you try to compute a mean, it's going to yield NA. NA.rm means it's going to toss those missing values before it tries to compute a mean. Okay, well, you actually anticipated precisely what the author was actually going to put. You may have wondered about the NA.rm argument that we used about. So he actually goes through and talks about the that we actually learned about that way in like the second class, I think. So we don't need to go through this whole thing. I did show you that there's an is.na function that allows you to turn an NA, create a new column that would say whether something is an NA or not, and true and false, and you can then use that to select. So having been introduced to this idea of grouping then summarizing, it can be useful to get some, the rest of the section goes into some useful functions and useful sort of summaries that you can take from a data set. So to do this, I though need to go back up to not canceled. So not canceled was created by taking the flights data set and filtering such that it kept those columns for which the row in depth delay wasn't NA, and the row in arrival delay was not NA. So presumably, so we're talking about flights, depth delay is departure delay, R delay is arrival delay. Presumably those flights that get canceled don't have a departure delay, nor do they have an arrival delay, so they would have NAs in there. So to get rid of those, you'd ask, is the value in this, for every row, is the value in this column NA? If it is, that will yield true. We want to toss those, so we put an exclamation mark to say not. So not on any logical value, we'll turn it to its opposite. So what this means is if it finds an NA in that depth delay column for a given row, it will toss that row. Ditto, if it finds an NA in the arrival delay row, it will toss that row. So not canceled, again, having all this is run and then assigned into an object called not canceled. I'll copy it into mine too. And I'm going to put these still on different lines so I can kind of see them. So this will create an object called not canceled, which will have only those flights that were not canceled, that actually ran. So he uses that. For example, here, if we want to look at, oh, this is just showing that when you've removed those columns, those flights where departure delay was NA, you no longer need to put or na.rm in your call to mean here. So it can be useful to get rid of your NA data ahead of time if you know it's there and you don't want to do anything special with it. There's some neat statistical things where you might actually want to try to infer from all the rest of the data that isn't NA what that value, that missing value might have been. In this case, with canceled flights or not canceled, that actually doesn't have a lot of meaning. But if you're, say, doing a battery of health tests on somebody and the person doing the tests or getting the test done didn't like the pressure cuff feeling, so you didn't get a blood pressure measure, then you might be able to infer from their height, weight, cholesterol, and other things what their blood pressure sort of should have been, and that might be a useful inferential question. So it's I just say that so to assert that it's not always the case that you want to toss NA values. Sometimes you actually want to do inference on those NA values. But
I think that's what I didn't mean, and there's a lot of NAs in the column, and you can't because the computation will see NA, and anything plus NA is going to
yeah,
be.
well, if it even sees one NA in the column, it's not going to yield anything.
Exactly.
That's why there's that is.NA argument to mean. This is just showing getting rid of those NAs at the outset. Then you don't need to worry about always remembering to put that is.NA or na.rm equals t. So let's see, what is this next one doing? It's taking the not canceled data. It's creating a grouping on that data using tailnum. Tailnum is the, let's see, let's look at planes identified by their tail number. So each individual plane. So each individual plane is probably in the data set a number of times doing lots of different flights. So this is saying look at each individual plane separately and do a summary on, for each individual plane, look at its mean arrival delay. So we can copy that. And that, the result of that is being put into, again, an object there. The summarize, again, it's going to include any of the variables that we're grouping by, as well as any of the variables that sort of are being computed in the call to summarize. So we've got tail num and delay. So this is the mean delay for this particular plane, mean delay for this other particular plane, and there's 4,000 different planes in the data set.
Is there a way to know all the different variables, just the headlines of the different variables in this data set? Like, I know we have 19 columns, so just the top row of the column. Like, I know there's
yeah. So you can either look at the thing there, do a view, and it shows all the things. Alternatively, anytime we've been showing these and we haven't been able to see all the columns, so you can look at the top columns there, see them all there, and it actually shows all the other columns, their names here. If you literally want to sort of create an object that that has the names of all the columns, there's a names function. So if I say names delays, it will grab the names from there. And you can do some computations on that now new vector of character strings, tail num and delay, if you wanted. Usually you figure out the names of things by looking at the output from just printing the tibble to screen or doing a view on the object. So having computed those delays, we can do like a little plot. So this plot here, I won't actually run it. You guys have seen calls to ggplot before, slightly different sort of spacing formatting, but freak poly is a geom that is just as a, imagine this as a histogram, but it's taken simply the height of each point in the histogram as, it's connecting the tops of the bars of each histogram along there. So it's in fact, oh yeah. So it's doing a histogram, so he gives it a value for bin width, but instead of having bars, it's just connected lines. I actually like the look of this a little bit better, though it somewhat hides how big the bins are. Critically, he points out that there are some planes that have an average delay of over 300 minutes. That's why there's even lines over here. So in our call to delays, we can, or our creation of this delays object, we're again getting not canceled, grouping by plane, getting a summary of the plane. We previously had already this part, getting the arrival delay. But what is this next part? N simply counts the number of entries that are in that grouping. So I'm just going to add it to this here. N equals, and you don't need to name it N again. Names for new columns and variables are humans. So N entries, I'll call it. And I'm not going to put it in an object called delays. I'm just going to print it to screen. So what this is doing is it's saying N is counting the number of entries in the original data set that are associated with each piece as specified by this group num. So there were 4 flights for this plane, 352 flights for this other plane, 145 flights for this other plane, etc. And I think he has a dot plot where he uses that information and he puts on the x-axis the number of flights that a given plane has taken, and on the y-axis the mean delay. And what's noticeable is that when a flight has only had a few, when a given plane has only had a few flights, there's a lot of variability from plane to plane in its average delay. But as you're looking at planes with lots of flights, there's lower variability. Anybody remember from their undergraduate stats what that principle is maybe related to?
How big is the denominator?
Yeah. Or I don't thought I. Sorry. Well, yes. Each dot represents sort of a given plane, and that plane's mean was drawn from a sample size of what's on the sort of on the x-axis. So yeah, that's the denominator in what though? So certainly the computation of.
Because you're having a large amount of delay in a small number of flights, so that's why you're having a higher.
Well, if you just said a large amount of delay in a small number of flights, you might expect that there'd be dots, and they sort of. The description you just gave describes dots up here and then sort of a line of dots going down this way. Why is it that like they're spread? The spread of the dots is bigger here than it is, say, here. Anybody remember this? Sorry? No, not, yeah, not, I don't think so. It's, I mean, I think the typical expression of it is it's the law of large numbers, that if you have lots of observations of something, your estimate of its mean is going to be very precise. So if I were to take the heights of 100,000 people, the mean I get from that is going to be very close to the mean I'd get if we observed everybody. So there's some true mean of heights out there. If I observed everybody at the same time, there's a true value for the mean height. However, if I don't have the time to do that, I might observe 100,000 people. That will, from attempt to attempt, yield a slightly differing value from the true mean. But those values are going to be much closer to the true mean than if I only measure 10 people. So law of large numbers, it's a corollary of the central limit theorem. But we're actually not going to need to talk about that ourselves in what we do. So I just thought you might remember it from your early days. So you can actually, so here he has a call where he creates this delays object and then he plots it. You can actually do it all in one. So you say delays. Actually no. He creates delays and he plots it. Here he creates delays, he filters, and then he plots the filtered version. So what he's doing here is he's saying, I only want to look at those flights. When I do my plot, I only want to look at those flights for which the value in the n column, we called it n entries, are greater than 25. So for the first little bit there, there's a bunch of flights that only had like one or two flights, and they are highly variable from one plane to another. Let's sort of zoom in, cut off all those flights where n is less than 25, and just plot those. So if you actually look there, it doesn't go all the way to 0. It's going to go just to 25. But this is the first time we've seen ggplot actually inside sort of a pipe stream. So ggplot knows about pipes, and instead of having to give it a data object, it will just accept the thing that it's receiving on the pipe as the data object that you want to plot. So a little less typing there, which is nice. All right. He shows some other sort of examples combining the use of all the dplyr tricks, so piping, grouping, summarizing, filtering, and combining that with some visualizations. You guys should look at those. Again, you can actually, if you want to quickly sort on things, you can use any of the dplyr stuff. So we've so far been showing pipes with just summarize and grouping, but all the dplyr will accept pipes. So doing this batters, pipe, arrange is the same as having an arrange with the first argument as .data equals batters. Not a lot less typing doing it this way, but it's kind of clear to yourself and readers maybe as you look at it later that we've got batters and we're doing something to it, right there. So he goes through some useful summary functions. So measures of location are useful, mean, median. There's some subsetting going on here. It's kind of like, well, let's actually walk through it. Takes the not canceled data. We're going to group it by year, month, day. And for every sort of unique piece identified by the combination of year, month, and day, we're going to compute a summary on the data on that piece of data. We're going to compute two things, average delay 1 and average delay 2. Average delay 1 is simply the mean of the arrival delay column. Average delay 2 is the mean of the arrival delay column, but with this other stuff put on the side of it. What these square brackets mean, it's another way to subset. It's in the same way that filter selects rows of the data. Square brackets can do the same thing. So what this is saying is, in this column called arrival delay, look, cut it up into, or only select those rows for which, again, the value in the arrival delay column is greater than 0. So altogether, this would only grab the delay on those. This would only grab the mean positive delay. So negative delays mean that it's arriving early, I think, the way it's structured. This isn't necessarily, I don't know why this would be of interest as sort of a metric. It's just an example of having this other way of subsetting, because it's kind of difficult once you've got to the group by and then summarize to then think about how you would create a filter that would allow you to do a summary on the full data set, on all the rows, but then another secondary summary on just those rows for which arrival delay is greater than 0. So you can use this sort of second way of subsetting the data. I've already shown you one other sort of metric you can use in your summaries, standard deviation. There's other measures of variability. So IQR, interquartile range, MAD, mean absolute deviation. There's other measures you can use, so min, if these can be useful particularly for finding, min and max can give you a sense of the range of the values that are observed in a given group or whatever. It actually could be useful on ungrouped data, give you a sense as to the range that all the data can take. Quantile will give you different percentiles in the data. So the median is the 50th percentile. Half the data fall above, half the data fall below. A 25th 0.25 quantile is the 25th percentile, the point at which half of the, or a quarter of the data fall below and 75% fall above. So you can select arbitrary percentiles by using the quantile function. The 0.25 is the sort of the probability point that you're using. And you can, let's see, measures of position. So if you just want the first entry in, so this kind of suggests that if you've already sorted using your arrange function, if you just want the first row in a given piece that you're looking at, you can use the first function, and that will grab the first entry in that column. Nth will allow you to specify, nth x2 means the second element. If that were a 3, it would be the third. If it were 4, it would be the fifth. 4, it would be the fourth. If you don't know, if you want the last item, but you don't know how many items are, if it's variable, how many items are in each piece, how many rows are in each piece, you can just say last, and that will grab you the last item in the column. So those can be useful. In range are filtering ranks. I actually don't. Min rank. I've never used min rank myself. I'm not actually sure what it's doing here. Let's actually see. So it's taking the not canceled data frame, grouping it by year, month, day. It's mutating, so it's creating a new column. In that column, it's getting the descended sorted departure time, getting the departure time that's, what is that? Here, let's run it with, I'm just going to run this bit. Okay, and I'll put these on separate lines. Okay, so it's grouping by year, month, day. I'm just going to group by year because that'll simplify things a bit, I think. Min rank, so run this, see what it gives me as a table. And there's something called R, so I actually want to select down to just, oh, actually, I want to do transmute. Just so I can see just that R column, not have all the other columns there too. So I've got year, and the rank. I wonder if this is telling me which rank has the minimum value. Is that? No, that starts in, I think, a half hour. Starts at 1, I think. I wonder. Yeah. Aha. Okay. I figured this out. This finds in the depth time column, it finds, I don't know why he says descend. Does this come out with the same thing? No. Nope, not the same. Descending. Okay, so the function, these functions are complementary to filtering on ranks. Filtering gives you all the variables with each observation in a separate row. Summarizing gives you one row per group with multiple variables. Yeah, I think it's, yeah, this is not well explained. I'll leave a little note for him that this section needs to be clarified, what the heck's going on. Because I think he's trying to say that here is a little bit more straightforward, where you can group by and you can say what is the first departure time and what is the last departure time. N is used to count things. If you want to count the distinct things, it's N distinct. So here's an example where he goes through looking at the flights that weren't canceled, grouping by destination, and asking, okay, for each destination, how many distinct carriers go to that destination or are in the data set for that destination. So that will show us the number of distinct carriers, and finally pipes that to a call to arrange, sorting carriers descending, yielding a table that shows all the destinations and how many carriers fly to that destination, with the first few shown, but the top ones being the first few shown. So Atlanta has 7 carriers flying in it, ditto Boston and CLT, anybody? Cleveland? I don't, no idea. Orlando, Tampa, I don't know these abbreviations. Austin is down there, maybe. So this process of counting, not the unique, but just using the N. If you do a group by, and then you summarize and you say equals N, is so useful, I guess, that he's created a sort of shortcut where this contains the grouping by and summary all in one go. So this is, if you pipe to a call to count, it's going to, for the column that you specified here, which could be multiple columns, it's going to count the number of sort of entries in the data set that are associated with that, each unique value there. So each unique destination, there's 254 not canceled flights that go to this destination, to 64 not canceled flights to go to this other destination, etc. The weight, I was looking at this earlier, I don't understand why that would ever be useful. For example, you could do this to count the number of total miles planed through. Yeah. It's kind of using count to sum the distances, which I'd rather be explicit and literally put a group by tail num and summary weight equals sum distance. This is not sensible to me. If you want to look at like the proportion of, here's an example where he looks at the proportion of departures that were early in the morning. So I think 500 is 5 a.m. We're grouping by year, month, and day, because maybe we're interested in just having those separate. And for each year, month, and day, so each sort of calendar date, we're looking at all the flights on that calendar date and asking what proportion of those flights flew before 5 a.m. To get the proportion, we would, well, sum doesn't make sense. That's a count. So we first do a logical. We say, look at the depth time column. For each row in the column, ask is that row entry less than 500. That's going to yield a bunch of trues and falses. If we count those trues, or if we sum those trues and falses, that gives us the number, the count of ones that were true. Alternatively, I think you must give it down here. If you take a mean there, that will give you the proportion of flights that were early. Here's an example where it does do a proportion, and he's asking, we're delayed more than an hour. So here, creating again column called hour percent. Should be prop because it's not actually percent. Arrival delay is greater than 60. If you take a mean of that logical statement, it's going to turn the trues into ones, the zeros in, the falses into zeros, and create a mean on those ones and zeros. So that ends up being a proportion of trues. So this yields the number, what proportion of flights are delayed more than an hour. And I think we showed, yeah, this actually, you can group by per day, summarize. Okay. So this is showing that if you have like multiple things that you're grouping by, so it's taking flights, it's grouping it by year, month, and day, assigning that into a new object called daily. If you do a summary on daily and just ask for each combination of year, month, and day, how many flights are on that? Each unique combination of year, month, and day. That gives you the per day or per calendar date summary or number of flights. That data set still has year, month, and day as columns in it, and now a single column counting the number of flights. If you then do a summary on this data set, it's going to no longer, it's going to like ignore this last, whatever is last in the list of things you're sorting by. So per day, it's recognized that we started off with flights, we grouped flights by these three things, and then did a summary on flights. So if we ask for yet another summary, it's going to assume that we want to be ignoring the last thing that we had in the original grouping. This doesn't seem like a I don't know. Do I think? I guess it makes sense. I don't see a scenario where I would use that. But this is simply demonstrating that if you were to iteratively go over and do multiple summaries, it will be peeling off. Like it will be sort of, it will be the first summary does all possible combination of these. The second summary will ignore day and look at all possible combination of year and month. And finally, the third summary will only look at year. It will ignore month. I don't really see much use for that. And finally, you can ungroup things. If like you grouped things at one stage and you want to ungroup them for some reason, you can do that. I wouldn't use that. Group to mutate and filter. Yeah. So you can filter based on features of each unique combination of things. This is going to still yield back a data frame with the same number of, this is a way of sort of getting rid of some rows as a function of the, yeah, well, it's saying, yeah, it only grabbed those sort of 5 worst, so longest arrival delays, 10 worst arrival delays. But do that for each combination of, or each sort of piece of the data set that's defined by the combination of year, month, and day. So for every year, month, and day, you're going to get down 10 rows that are sort of the worst delays experienced on those days. But this is yet another one that's not super useful. So that's actually all I wanted to get through today, because next week we're going to jump down to data importing. Yeah. So all these uses of dplyr, they're useful for sort of getting a feel for your data. Once you've got your data read in and in a decent format, so tidied up, these allow you to get a feel for the general properties of your data if you didn't sort of have good expectations going in. Usually when you're involved with a project, you know sort of what to expect in terms of the ranges of the different variables and I guess if you're got sort of ongoing data collection, say you're collecting sort of lots of biometrics from lots of different people, you might want to be able to get sort of a quick sort of where is the general mean heart rates and what is the variability, and maybe be able to identify outliers and things like that. So yeah, this is a way to sort of get a sense of your data, both if you don't even have a good sense of what the variables are coming from, but also if you do know, but you want to keep track of like checking for outliers and things like that. All right, well, early class.